Hello, and welcome to Lecture 3. This is Geography 102, Transforming the Global Environment, and once again, this is Paul O'Keefe from the Department of Geography at Rutgers University. Slide 2, just beginning with the very straightforward course description. I'm going to go back to this again and again and re-emphasize this idea that at the heart of this course is an attempt to know better and know deeper and know more complexly the relationship between human activity in the natural world. In the next few lectures in Unit 2, we're going to look specifically at climate and climate change, the role of humans in causing it, what climate change may mean for society, what it also may mean for the environment. In this class, and in all the lectures, to the best of my ability, towards the end of the semester, I'm going to try and structure them in a similar manner. I'm doing this so you see how I flow through the class, but also as an attempt to construct this integrative, critically understood relationship between people and the environment, between humans and nature. So in each class, I'm going to try and begin with the environmental science that underpins specific issues. This might be the climate system and the science of climate change that underpins issues of climate we are looking at now. It might be the science of population change, of population growth and decay. It might be the science of resource access, of resource use. The social sciences of economics come in later. It might be the science of where food is produced. It may be the science of disasters, of earthquakes, of tsunamis. There is a consensually agreed upon body of environmental science and knowledge that we need to understand before we can even begin to appreciate the role humans have in transforming and affecting it. We are then going to introduce the various ways in which socioeconomic activity produces or contributes to these problems, whether that's carbon emissions driving climate change, whether it's certain societies having much higher birth rates than others, whether it's the role of food waste, both in the wealthy and poor parts of the world, whether it's the question of why people die from similar types of hazards in different amounts across the world. Why? Where is environmental risk most felt? Where is it not? Why is this happening? And then in each class, I'm going to think through what this means for the environment, the ways we are using the environment. Are we leaving a world without adequate resources? A world much dirtier than we have in the present? A world where it's much more difficult for people to feed themselves? Or are we possibly leaving a better world where we know the value of forests, of clean air, of clean water? And to flip it once more, what does this mean for society? Is the way we use and sometimes abuse the environment now, does that threaten our future way of life? Are there ways in which we can live not just with a cleaner environment, more sustainably, but also live in a society that can improve? Ultimately, the question we are looking at is that of what is to be done. So as I move on to slide 4, just to quickly sum up, in the class so far, we've looked at the syllabus and we've looked at geography, the reasons why this course is part of a geography degree. I've touched a tiny bit on what geography at Rutgers offers. If you want to look more, please email me. I've introduced the idea of the Anthropocene. I've introduced the idea of the world as a system, an interconnected system. And I introduced the limits to growth as one way of understanding the human-environment relationship. Today we're going to begin focusing on weather and climate. Climate change in particular is argued by many to be the most pressing global environmental issue. But first, as I suggested before, I'll go through some of the basic science. And for this involves looking at what weather is, what climate is, and then a bit more focus on what the difference is and why it matters. We'll then look at some of the global drivers of climate, and we'll finish today's class by focusing on the ways in which the climate's changing and the role of human activity in this process. So I have in class so far, and I'll continue to emphasise the centrality of human-environment relations to this course. You'll get sick of this phrase, but I think it's so important. In all ways, we're trying to think, do we always treat the environment the same way? Are there reasons why we tend to use the environment in certain ways? Is the way in which damage is both observed but also fixed variable across the world? All this in the context so far of broad global human environment relations. In this unit, we will focus specifically on the issue of climate. Associated with this lecture are two fairly short readings. There's this primer that was produced by NASA on the difference between weather and climate, which should help reinforce some of the things I'm going to say, and a short cartoon which demonstrates temperature changes over the past few thousand years. So slide 6, just to keep on track, we're just going to quickly define the weather, we're going to define climate, and then the difference, and why does it matter, as I've said. Because climate and weather are not the same thing. They're often confused and they're often mixed together in public understandings of climate change. Famously, a Republican senator from the South, James Inhofe, stood on the floor in Capitol Hill waving a snowball around, saying it's snowing outside. How can climate change be happening? That's getting weather and climate change mixed up. That's a warm day in January. It's a wet, cool day in the summer. It's snow in April. Weather events. Weather is daily, sometimes weekly, but even a week ahead, we can't predict with 100% accuracy what rainfall or temperature will be in a week's time. Climate, on the other hand, refers to much longer-term patterns derived from long-term weather data. This data is usually over a period of at least 20 years, but usually 30 years or more. At the heart of climate are simply two measurements, that of average temperature and average precipitation, which is rainfall, but also snowfall, sleetfall, freezing rainfall, icefall. These two together, their variations across the Earth, explain to a large degree different climates. Climate is driven ultimately by the sun, but in particular it's the relationship between different locations on the Earth's surface and the radiation they receive from the sun. Other factors come into play, including things like continentality and altitude, which we'll explore. But just to re-emphasize, we're going to really focus on climate in this class. I'm going to introduce the basics of it. If you want to study these issues in more detail, I strongly recommend Geography 101 or possibly other courses in other departments. So weather, just to sum up, is a snapshot. Captures the day. This is a surface map. It's from a while ago. From weather.com, you can see the fronts, you can see clouds associated with rainfall on the map, you can see areas of low pressure, you can see areas of high pressure. Isobars on the map indicate areas of equivalent pressure. Climate, on the other hand, is the long-term patterns of weather. Weather, in this case, indicates an area of high pressure above Kentucky and Tennessee. Is this an area that typically sees high pressure? Well, not necessarily. The long-term patterns bear this out. Weather is highly variable. On the other hand, climate is much less variable, as I've said. It's about the long-term weather patterns. For example, what is the average rainfall in New Jersey in April? What's the average daytime high in July in Piscataway? What's the average winter temperature in Miami, Florida? With long-term data patterns, we can begin to reliably understand these things. And as I mentioned before, At the heart of the Earth's very variable yet interconnected climate is the relationship between the Earth and the Sun. So the next slide, slide 11, will go into this in detail. Related to this, and things that explain different climates across the world, are some other factors that we'll explore. One is the distance from the equator, which has a strong relationship with the average temperature in different parts of the world. We'll also look at the presence of the intertropical convergence zone and its importance, especially with regard to precipitation patterns. We'll look at the issue of continentality and how even in places on a similar latitude, a similar distance north or south of the equator, as others can have vastly different temperatures and climates based on this principle. And we'll also touch on the question of altitude. We'll sum up by looking at how the world's climates vary and emphasize some of the important ones. So slide 11. And this diagram is pretty fundamental. It may be very familiar to you. If not, I guarantee it will be by the end of the course. At the heart of understanding the global climate system is understanding the Earth-Sun relations. Now, this is not about how near or far the Earth is from the Sun. That does vary from the year, throughout the year. And actually, you may not be aware that at certain points of the year, the Sun is much closer to the Earth than at others. In January, roughly, at a period known as perihelion, the Earth is at its closest to the Sun. It's about 5 million kilometers further away from the Sun in July. But as I said, the climate's not about the distance from the Sun. It's about the angle the Earth makes in relation to the Sun. And as this angle changes throughout the year, we see very different patterns. This angle changes because the Earth does not rotate on an axis that is vertical. It's at an angle of 23.5 degrees from the vertical. The far right globe shows this. The Earth doesn't point north. So on the far right of the diagram, the winter solstice, you see the Earth is tilted 23.5 degrees from the vertical. It's tilted away from the Sun in what's called the winter solstice, December the 21st to 22nd, clearly entering the northern hemisphere winter. As the Earth continues to move around the Sun throughout the year, as well as rotating on its own axis for day and night every 24 hours, we see the angle change. At the opposite time of the year, so on the left of the diagram, we have the summer solstice, where the angle of the Earth is tilted towards the Sun. At this point, we see that the northern hemisphere receives the greatest solar energy it receives, as per the diagram. Halfway between the summer solstice and the winter solstice, in both the spring and the fall, or the autumn, as we call it back in Britain, we find that the Earth is neither tilted towards, as in the summer solstice, or away from the Sun, as in the winter solstice. In fact, all parts of the Earth are receiving equal amounts of incoming solar energy. So we have this pattern repeating through the year. And I just want to make a couple more observations about this diagram. If we look at the winter solstice, we see the North Pole and the polar Arctic Circle. This is anywhere north of 66.5 degrees from the equator. Conversely, in the southern hemisphere, we have the Antarctic Circle 66.5 degrees south to 90 degrees south. So in the winter solstice, the Arctic Circle is tilted away from the Sun. And because of this tilt, the Arctic receives zero sunlight. This is why it's in perpetual darkness for almost 3 months of the year, because of the Earth's tilt. You see the opposite in the summer solstice on the left of the diagram. The Antarctic is pointed away from the Sun and receives no sunlight and therefore no daylight. In the winter solstice, because of the Earth's tilt, incoming solar energy is greatest in the southern hemisphere, above what's known as the Tropic of Capricorn. In the summer solstice, the incoming solar energy is greatest above the Tropic of Cancer. The area between the Tropic of Cancer at 23.5 degrees north and the Tropic of Capricorn at 23.5 degrees south is perhaps, obviously, the tropics. This is where we find tropical climates. The equator at 0 degrees latitude, because it's neither north or south of the equator, typically receives the most energy on average throughout the year. So just to sum up some of those points, around the June 21st summer solstice, the northern hemisphere is tilted at its maximum towards the sun. The opposite occurs at the winter solstice. The vernal, the spring, and the autumnal, which is the fall equinox, we find that the Earth is neither tilted towards the sun or away. At these times of year, you would find that, give or take, every part of the Earth receives 12 hours of daylight, 12 hours of night. More broadly, these Earth-Sun relations explain the basis of seasons. So we have these relations, and they are critical. And the first thing we can begin to build in terms of knowledge of climate is how they affect global temperature. And the distance from the equator is very important in what is known as the average temperature of the world and different parts of the world. This map shows throughout its center what's called the heat equator. And the idea with this is that the colours, the darker the orangey reds, the warmer the average temperature, moving through yellows to greens and dark blues, where the average temperature is coldest. And you see the heat equator is broadly in line with the equator. This is the point of the world where the average temperature throughout the year is highest. And you see as we move both north and south, there's a fairly regular pattern by which the average temperature reduces. It might be warmer at certain parts of the year, but it might have a colder winter, or it might just be colder year round. This broad pattern of global climate, that as we move away north or south from the equator, the average temperature drops. So there's the major take home from slide 13. Slide 14 is going to see me try and introduce where rainfall comes from, very straightforwardly, and the relationship between the distance from the equator and rainfall. It's not as straightforward as temperature. That previous slide you saw, you move away from the equator, the average temperature falls. With rainfall, it's different. And we're going to begin at the equator. The equator is the location of where, broadly, the intertropical convergence zone exists. And this is fundamental in understanding where precipitation occurs. And so you see on this diagram towards the right what are called the Hadley cells, and especially the movement of arrows, the yellow arrows, around the equator. The movement away from the Earth of air, eventually forming what I've mentioned are called Hadley cells. I want to go ahead to slide 15 to look at this in some more detail. This slide has the equator toward the right, and you can imagine a typical equatorial climate. It's hot all day. The sun is heating the earth. The air is rising. Eventually, the air begins to cool as it rises, and moisture within the air condenses, it forms clouds, and eventually falls as rain. This typically happens in equatorial regions throughout most of the year, as we'll see. After the rain has fallen, we now have dry air, and we have air that begins to move across the earth. It then begins, as it's cooled and moved, to sink. And I'm going to jump back to slide 14, because we can see again on the right of this diagram the yellow arrows. Air that originally moves up into the atmosphere around the equator spreads out and begins to sink north and south of the equator in areas that are known as subtropical highs. We're talking in terms of highs here, in terms of pressure. Around the equator is typically low pressure because precisely of this process of air being heated and the earth being heated and air rising very fast. Imagine the air leaving the earth. The pressure is much less than if the air is sinking down, as it tends to do at subtropical highs north and south of the equator. Going back to slide 15, you see what happens. On here it's marked as the subtropical jet, and below, the sinking air drops to the ground, but this air doesn't have the moisture that we see in the equator. This air is dry, and this air sits on the ground. This is high pressure systems associated with dry weather, and on a global scale, going back to slide 14, you can see around the subtropical high is areas on this map of North America, like Mexico, parts that are very dry, and in South America, the west coast, the Atacama Desert, amongst the driest places in the world. This air then rushes again north and south from the subtropical high. And going back to slide 15, we can see how therefore the Hadley cell forms. Air moves from the subtropical high at roughly 30 degrees north and south of the equator back to the equator. This is because of a fundamental physical principle, summed up in the cheesy little rhyme that air blows from high to low. The direction is down a pressure gradient. Just like if you let out a balloon, the air rushes out from the pressurized interior into the room. You do it with a helium-filled balloon. You entertain your friends. The air rushes out, the helium rushes out. On the Earth's surface, air follows the same patterns, and the distance over which this pressure gradient, the air moves, is to a large extent the wind speed. If air moves over a pressure gradient over a smaller geographical area, then it's moving faster. But typically it will always move from areas of high to areas of low. Going back to slide 14 to summarize this, we then see that we have the formation of Hadley cells, where air is moving from the subtropical highs to the equator. It's then rising at the equator and typically falls with a lot of rainfall there. And then the dry air moves north and south and sinks. These are the Hadley cells. We see patterns continue further north and south of the equator. Areas of low pressure develop generally in mid-latitude regions north and south. As we get towards the Arctic and the Antarctic, we find areas of high pressure. But the absolute major takeaway I want you to get from this diagram is the idea of the intertropical convergence zone. This occurs at the place where the Hadley cells north and south of the equator meet. On this idealized diagram here, it's roughly on the equator, the place, the low pressure location where air from the subtropical highs moves towards. And the intertropical convergence zone is where the hot air meets and where the hot air rises and where we get subsequent cloud formation and precipitation. What's very important with this, and it ties back to the Earth-Sun relations, is that this moves throughout the year. And it's this movement that affects a huge amount of where rainfall happens throughout the world in different places. So as well as this broad trends going north from the equator is usually low pressure, typically associated with rainfall. The subtropical high is typically high pressure, drier areas. Further north again, between latitudes of about 35 to 45 degrees north, low pressure areas associated with moisture. And as we reach the North Pole, it's an area of high pressure, an area where there's surprisingly little rainfall or snowfall. Very straightforwardly, the ITCZ moves north in the northern hemisphere summer and moves south in the southern hemisphere summer. It forms where the two Hadley cells meet, and from this we can begin, as I've said, to explore global precipitation patterns. So the next slide, which is slide 16, shows these patterns, and it begins showing the average precipitation in the month of January. Dark blue areas are receiving the most rainfall. White is almost zero rainfall. And you see these global patterns across the equator. It's blue, Southeast Asia in the right, much of Central Africa, and then the Amazon, South America, in the left of this map. That's a typical pattern in January. What I want to look at is how these patterns vary through the year, because you can really grasp the movement of the ITCZ north and south. So hopefully this animation's going, and I think it is. And we see throughout the year patterns, and as we're going to circle back around to January, we're going to see moving into the northern hemisphere spring and summer, the location of dark blue is moving further north. As we move into the southern hemisphere summer, it moves south. What this is the movement of the ITCZ tracking the part of the Earth which is receiving the most energy from the sun. The consequence is that the ITCZ forms here and we get rainfall. So in the northern hemisphere summer, we see in Central America, towards West and North Africa, we see the monsoon of Asia. November, December, we see rains in South Africa and Australia. This pattern is continuing throughout the year. So just based on these fairly simple Earth-Sun relations, it's not complex science, we can ascertain some broad global characteristics about the climate. Around the equator, we typically get hot climates because the sun is shining its energy here on average more than anywhere else. But it's also wet for precisely the same reasons. As the ITCZ moves north, the equator is still touched by it. As it moves south, it remains touched by it. About 30 degrees north or south of the equator, we hit the subtropical highs, where the climate is still hot. We have hot air, but it's the sinking, dry air. The high pressure means that it's dry. As you saw on the previous map of precipitation through the year, the areas between the equatorial the equatorial climate and then the subtropical high, between the Amazon rainforest and the deserts of Mexico, is very much a transition. As we continue to go north or south of the equator, we hit the mid-latitudes, which have a whole range of climates, but are typically wetter than the subtropical high and the polar latitudes. And in some places might be cool, in some places hotter. As we get to the far north and far south of the Earth, we find that the climate has reverted to being cold and dry. It's known in parts as tundra, the polar desert. And slide 18 shows these climates and their geographical distribution. And again, there should be some fairly immediate links back to rainfall patterns. You see the dark green on this map is what's called a tropical wet climate. No dry season. An average temperature in the 60s and rainfall in the bare minimum, tens of inches a year. There's no dry season, so there's adequate water in most of these places year round. As you see, this is the Amazon, it's West and Central Africa, and it's Southeast Asia. North and south of here, you see the kind of lime green colour, the tropical savanna. This is the influence of the ITCZ. This is part of the year being a rainy season, part of the year the dry season. The rainy season associated with the movement of the ITCZ. If you've ever watched a nature documentary about the Serengeti, the Masai Mara, the movement of the wildebeest from Tanzania to Kenya, they're basically following the movement of the ITCZ. There's also the famous documentary The Lion King, which captures similar processes. They're following the rains. The rains cause the grasses to grow. They provide the food for the wildebeest, and they move. Right? North of the equator, we typically have a rainy season in the northern hemisphere summer. South of the equator, the opposite occurs. Again, as you move further north, further south, the browny orange on this map, the arid and the semi-arid climates. Right? The Sahara Desert, the Kalahari of southwest Africa, much of interior Australia. It's arid or semi-arid. That's dry or semi-dry. You see the influence of these global patterns. And then as we move further north, because remember there's much less land mass south of the equator at the mid-latitudes. We have a range of climates from humid subtropical in the southeast of the US into more continental climates. Other parts, especially coastal areas, have what we call a Mediterranean climate. Places linked, unsurprisingly, the similar climate of southern Spain, of France, of Italy, of the North African coasts, of southern Australia, of southwest California. Unsurprisingly, similar things are grown there. The links here with the climate is where wine comes from. The far north and south of the Earth have polar climates. Cold, often dry. The water where it exists is inaccessible in the form of ice. A quick word here about highland climates. Globally, we might look at the Himalayas of Asia, the Plateau of Ethiopia, the Ruwenzori of Africa, the Andes of South America, the Rockies, the Alps in Europe. Marked on this map as highland climates. The reason these have their distinct climates is precisely because of their unique topography and physical geography. There's something called the environmental lapse rate. In metric, what it means is for every 1 kilometer, 1,000 meters, you go up in altitude. The air temperature drops by 6.4 degrees Celsius. In American measurements, for every 1,000 foot you go up in altitude, the air temperature, all other things being equal, drops by 3.5 degrees Fahrenheit. You'll have seen this if you've ever, as I do, ignore the movies on the aeroplane and just watch the flight plotter thing. Yeah? The temperature drops as you move up. So, on a global scale, this is important, because if you're 10,000 foot up in the Andes, in the Himalayas, then regardless of anything else, the air temperature is going to be 35 degrees Fahrenheit cooler than somewhere on the same latitude, perhaps, but at sea level. If you're 15,000 foot up, it's going to be, over 50 degrees cooler. So highland climates by themselves and their exposure to the direct weather, their exposure to climate, means that they have very distinct climatic factors themselves. But that's all I want to say about highland climates. What I do want to focus on, and where slide 19 is going, is the concept of continentality. Because this is something that confuses and makes more complex ideas of where on the Earth gets global, get different climates. This isn't, it isn't totally contradictory to the other things discussed, but it is a different issue. And what we're looking at here, at the heart of it, is this role of land and oceans and the difference they have in mediating temperature, especially in mediating the worst of winter cold, but also the most extreme summer heat. This is the role of the oceans. If the opposite occurs, and you live thousands of miles from the closest body of water, you'll find that continentality is a factor. And what continentality does means it tends to be much, much hotter in the summer and much, much colder in the winter. Now, before I introduce two Russian cities that's shown on this map, it's quite hard to see, Murmansk up in the northwest of Russia, and Yakutsk way in eastern Siberia. I just want to give an analogy that might help. Consider a pot on the stove, just a big cheap pot you bought from the Dollar General. So it's not the world's best quality pot. And it's got nothing in it, and you turn the gas on, right? And the gas will heat that pot up really quick. you've probably got 30 seconds before it's too hot to touch. And you keep heating it up, it's going to get hot and hotter and hotter. Probably start smoking. It's cheap enough, it might even melt. I've bought some pretty poor quality things from the Dollar General. Also some very useful things. But I digress. Now consider the same pot full of, a gallon of water. Pot's still as cheap and flimsy as earlier, but you turn it on and it heats. But you could have your hand in that water for minutes, depending on how powerful the gas stove was. It would slowly heat up. And in both those scenarios, you cut the gas. Yeah? What you see happening first, in the empty pot, is a rapid cooling. It heated up fast, but it cooled down fast. That pot of water is going to remain hot for a long time. The same principle is playing out across the Earth in terms of the climate, and the same principle is at the heart of what we call continentality. So Murmansk and Yakutsk are the two cities we're going to compare to see this impact of continentality. So Murmansk is more northern than Yakutsk. So based on the heat equator map we looked at, we might anticipate it being colder. But they're both fairly northern cities. And we're going to compare them by looking at two climate graphs, and we'll see precisely how continentality impacts different places. So Murmansk is on the left of this diagram, and this shows two different aspects of climate. The red line indicates temperature in both Fahrenheit and Celsius. The blue bars indicate rainfall in millimeters. But it's the range and the pattern rather than, and actually with continentality the focus is mainly on the temperature. So we see the scale on the left for Murmansk. The months are 1 through 12 rather than January through December, but in January we can see that the average temperature in Murmansk is about 14 degrees Fahrenheit, give or take. By the 7th month, July, we see the average temperature has risen to about 50 degrees Fahrenheit and drops off again through the fall. So what we're looking at here is a range from the coldest to the warmest part of the year of about 35 degrees Fahrenheit. Not a huge range. I'm sure a lot of you have witnessed that in a day here. I certainly have. Now compare this to Yakutsk. Remember, Murmansk is on the coast, by the ocean. That ocean that heats up slowly through the summer, a little bit, and it gives its heat off as we move into the winter, and then absorbs a lot more heat, more slowly than the land as the summer heats up. Compare that with Yakutsk, thousands of miles away from the ocean in the middle of Siberia. Similar latitude. So going just off latitude, distance from the equator, we might anticipate a similar temperature to Murmansk. But because of continentality, we see a couple of things. We see in January that the average temperature in Murmansk, and I don't know if you can make that out, is negative 40. It's negative 40 Fahrenheit, that's negative 40 Celsius. It's one of the places they meet on the scale. Negative 40. Come this peak temperature in the 7th month, July, we've hit about 68 Fahrenheit. What we're looking at here is a range of climate change throughout the year of almost 110 degrees Fahrenheit compared to 35 degrees in Murmansk. This difference in range is the importance of continentality. Not just Russia, this is why Minneapolis, why Chicago, the Dakotas have those miserably cold winters, but also really hot summers. So climate is more complex than simply how far from the equator you are. And climate, as we move towards the last part of this class, has become increasingly important. I've just tried to outline some of the basics of it. But what I'm going to show on the next slide is evidence towards this claim. The global average temperature is increasing, and it's increasing at a rapid rate. So slide 23 shows the global temperature change, or will when I begin it, over the past 160 years. Now, just before the animated graph starts functioning. Take a look at it. We have the 12 months in a circle running around the outside. And what we have are 166 different years of measurements of average global temperature. And in each year, we have an average monthly measurement of global temperature. And from those, we can add them and we can analyze them and we can work out what the average temperature is for any given month. And what this graph's going to show, beginning in January 1850 to February 1850 to March 1850, every month, all the way through to the present, there's going to be a plot on this graph. And if it's right in the center, it means that the average temperature of that month in that year was average, right? 0.0 degrees away from the mean on average. It's just the average. But increasingly, average temperatures, have been shown to be rising, and increasingly rising rapidly. And we're about to see this. So beginning in the mid-1850s, we see the temperature plots, and they're broadly around the average, sometimes a little warmer, sometimes a little cooler. We move into the 20th century, and we begin to see warming. In the latter half of the 20th century, it increases somewhat, but it's the 2000s, the last 10 years of measurements, that are beginning to scare people. Because it seems that with every passing year, the temperature is rising. And with every passing month, we are seeing records set. We are seeing the temperature on average globally being much higher than the last 160 years of average temperatures. This is what people are very concerned about. This is the evidence of the warming climate. This is the fundamental basis why people are fundamentally scared about what this might mean for the future both of the Earth but also of human civilization. Is this process going to continue? Is it going to limit growth, whether that's economic growth, whether that's broader societal growth? Is it going to eventually stop us from functioning? At what point will this warming continue? Where we are now, and again, this is a very straightforward statement, but for this class, this is the position we're taking. Right? The global average temperature is increasing, and we simply can't justify and can't fully explain this increase by recourse to natural climatic variability. So you're going to have a little read at what's pretty much a comic to just explore this a bit further and just see how really extraordinary the last few decades have been in the context not just of the last 160 years. I'm actually just going to go back to this diagram because this is based on the actual temperature record. We have 160 years or so of accurate temperature records. But using various measures like ice cores and tree rings, people have gone back into the past. And doing that, we see that what's happening now is very much extraordinary. This change is so rapid. So have a read, if you haven't already, of this comic, just to place this warming into a context. Think about the Anthropocene. Think about why people are concerned that this is an increasingly important problem, and if we don't do something about it, we risk major change. And just as we begin, not just to wind down this lecture, but set up for the next few lectures, even immediately now, the question, well, how much is it going to warm, is only to some extent about understanding the environment. It's hugely dependent on society, because we know, and we'll explore this in lecture 4 in much more detail, that at the heart of climate change is the emission of carbon dioxide. And at the heart of carbon dioxide emissions is societal activities. And depending how we act into the future, and this returns to the themes of lecture 2, the representative carbon pathways depend on not just how we operate socially, how we get from A to B, how we get goods around, how we live our lives, but also the type of climate we can expect. The more carbon, the more warming. And if we expect to hope to keep warming below 2 degrees Celsius, even though we're already seeing, as that image showed before, rises average monthly temperatures 1.5–2 degrees Celsius warmer already than the average we have, then we pretty much have to start reducing emissions immediately. On the other hand, if we're happy with a continuing rise in temperatures, we can continue to emit. We look for new sources of fossil fuel. We reopen the coal-powered plants. We put miners to work. We do these things. We'll have a different world. We'll have a different set of jobs, a different set of rich and poor. But we'll also have a completely different amount of carbon being emitted. And the suggestions for what this might mean in terms of the difference based on social activity are really quite incredible. The representative carbon pathway 2.6, this is the low estimate, holding the world to below 2 degrees Celsius of warming. The top estimate is so many magnitudes larger. We're looking at between 7 to 9, possibly up to 15 degrees Fahrenheit warming on average in parts, especially of the polar regions, which again we'll come back to in lecture 4. But this isn't, two images we look at and say, ooh, I wonder which one nature will choose. They're two images that give us possible futures. And we have choices about which one we want to work for or which one we want to avoid. This is why the science quite often immediately becomes political, because we get there not by understanding the science better, but by taking certain actions, certain steps, moving in certain directions. With that, I'm going to wind down this lecture, and I'll see you again for lecture 4. Thank you. This was lecture 3, Weather and Climate, from Geography 102, Transforming the Global Environment.